grew up in London, and she did her undergrad at Cambridge University in physics. It was part of the natural sciences department. She did her graduate school at Oxford University in particle physics. And one interesting thing to note is that in her group or her class of particle physics, there were 14 people and 6 of them were female, which is something I thought was really interesting. And also, one other interesting fact is that it takes about 3 to 4 years to complete a PhD in Oxford. Yeah, that was cool. She was in Philly for 3 years before coming to Cal, and she said she doesn't miss the winters. What she does miss is her Morgan. So it's a British sports car that unfortunately doesn't meet with the emission standards of California, so she can't bring it. It's really cool looking. I saw a picture of a similar car. She likes the weather at Berkeley, and it's quickly becoming one of her homes. And apart from that, she enjoys drinking black tea. She brings it all the way from England. Eating British chocolate and English cheddar cheese. Everyone, Professor Gabriel Orebi.
Good afternoon. I'd like to thank Sydney for inviting me to be here, and Anna for that lovely introduction. So I'm going to talk about the snow plus experiment and the precision era of neutrino physics. So just to give you a brief overview of my talk, I'll start by introducing the neutrino, for those of you who may not be familiar, and then how it fits into the standard model of particle physics as we understand it today. I'll then focus on the solar neutrinos, and in particular the historical solar neutrino problem. And from there, I will summarize the status of neutrino mixing as it currently stands, which will lead me into where we go from here, and how the Snow Plus experiment can help us with the view. So it's 1930, and Pauli is scratching his head because beta decay has been observed, but the outgoing electron appears to have a continuous energy spectrum. And this is posing a challenge because it makes it difficult to conserve both energy and momentum simultaneously. So Pauli did something very brave. He postulated a new particle. This particle, he said, would have to be massless so that it could carry away any fraction of the total energy of the decay. And it would also need to interact incredibly weakly, so that would explain why we hadn't detected it yet. So this was a fairly brave thing to do. And he actually didn't fancy going and doing this in person, so he sent a letter to the conference saying, I've done a terrible thing. I have postulated a particle that cannot be detected. So it actually took another 2 decades before neutrinos were detected. They were detected in 1956 by Rines and Cowan at the Savannah River nuclear reactor. What they actually saw were antineutrinos, which are the antimatter partner of the neutrino. And the nice thing about antineutrinos, which are produced in the nuclear reactor, is they actually give you a double coincidence signal in your detector. So this is a very nice tag for a neutrino event. The antineutrino comes in, it interacts on a proton in your target, and from that you get a positron and a neutron. And the positron gives you a prompt annihilation signal, and the neutron wanders around in the detector for a little while before capturing, so you get a delayed signal. So, having detected neutrinos and being fairly convinced of their existence, we would now like to fit them into the standard model of particle physics. So I'm skipping quite a bit of history and showing the model as it stands now. So we know that matter is made up of fermions, which are spin-1/2 particles. And these fermions are separated into 3 generations of these invertible lines according to mass. The fermions come in 2 categories. There's the quarks, which are charged, they're massive, in that they have mass. And they're also colored, which means they can interact via the strong interaction. Then there's the massive leptons, the electron, the muon, and the tau. These are also fermions, spin-1/2, and they're charged, negatively charged, but they do not carry color, so they only interact weakly or via the electromagnetic interaction. And then finally there's the bosons, which are spin-0, which mediate the different forces by which these particles interact. So we know that the neutrinos must be weakly interacting, so we slot them in neatly here, and originally they were thought to be massless, and you know, it would be nice, we know there are 3 charged leptons, it would be nice if there were 3 neutrinos. 1 per generation. In fact, it was shown that this was the case with measurements of the width of the Z boson. So the Z boson can decay to anything that is less massive than itself. So by measuring its width and looking for anything that we don't already know about, you can determine how many light neutrinos there must be. And the data very clearly fit the hypothesis of 3.
What is being plotted there?
I'm sorry, this is the center of mass energy, and this is the cross-section. So this is data from the different experiments and what it would look like for 2, 3, or 4 neutrino species. So it very clearly falls on the line for 3.
Is this the cross-section for wave collisions?
Well, so this was from, I think this was lab, so it's electron, proton. But I mean,
Electron positive.
Sorry, electron positron. But it doesn't actually matter. You're just looking at the decay of the Z. So however you produce the Z, you're looking at the products.
That's a cross-section of what in light?
Electron positron. So we're fairly convinced that there are 3 neutrino flavors. So of course we would like to see them all. And this we have now done. Electron neutrinos, these are produced in the sun and in nuclear reactors, as I mentioned. Bryce and Karen have seen them already. Muon neutrinos, these are produced in cosmic rays. So in the atmosphere, when the muons decay, they produce muon neutrinos. And we can also produce these in man-made beams. And then in 2000, there was the first observation of the tau neutrino, again from man-made beams. So I will focus for a little while now on neutrinos from the sun. The standard solar model tells us that the sun is powered by nuclear fusion. The hydrogen in the core of the sun is fused into helium, and in doing so it produces a huge amount of energy, that's the heat and the light that we see from the sun, and also neutrinos. So one way to verify that we actually understand what's going on in the sun is to look for these neutrinos. And just as an aside, you know that your field is getting interesting when Hollywood immortalizes it on film. Some of you may have seen the film a couple of years ago. It's called 2012. In this film, solar neutrinos caused the end of civilization as we know it. This happens in December of this year. And the premise is that some particularly active solar flares cause the flux of solar neutrinos to spike dramatically, and these neutrinos start interacting with matter. They cause the mantle to destabilize, the tectonic plates shift, cue death destruction disorder, your Hollywood disaster film. So we'll come back to this, but first we need to understand a little more about solar neutrinos. So neutrinos are produced as a byproduct of the fusion reactions that power the sun. There are 2 cycles of these reactions. There's the PP chain, which is the primary source of solar power, and then there's the CNO cycle, which contributes about 1% of solar energy. Neutrinos are produced in several interactions in these chains. There's 5 different interactions in the PP chain, and then the CNO neutrinos, although these have yet to be detected. The neutrinos from the different interactions can be distinguished by their energy spectra. So the energy spectra shown here, this is a log scale on both axes. The solid black lines are neutrinos from the PP cycle, and the names are the different reactions that they come from. So here's the boronate neutrinos, for example. And then the blue dashed lines are the CNO neutrinos. So a number of experiments have sought to look for these neutrinos. The early experiments were what we call radiochemical experiments. So they use a large volume of some liquid, and they look for neutrino interactions on the target. They run for some period of time, and then what they do is, for example, chlorine experiments look for neutrino interactions on chlorine, which produces argon-37. Argon-37 actually decays, so after some period of time, you assay your detector and determine how much argon-37 you have, and that tells you how many neutrino interactions you had. So the chlorine experiment was Ray Davis in the Homestake mine in South Dakota, a Nobel Prize winning experiment. And then there's been several gallium experiments. This is nice, has a very, very low energy threshold. But the downside of the radiochemical experiments is that because they do this integral measurement, you can't distinguish the different neutrinos. You just make one measurement of the total number of neutrinos over that time period, and you can't tell individual energies or a time series or anything. So along came the water-Cherenkov experiments, Kamiokande, super Kamiokande. The idea here is that you have a large body of water, and when the neutrinos pass through the water, they can interact with the electrons. They just scatter. But the outgoing electron can actually produce Cherenkov light in the water, and you surround the water with photomultiplier tubes. This is a huge array of photomultiplier tubes which can detect that light. So this is the inside of super Kamiokande, which is 50 kilotons of water surrounded by photomultiplier tubes. It's fairly big. And for comparison, it's a little bit dark, but Hollywood's version of a water Cherenkov detector from 2012. So here they are coming to look at their detector. The water is down here, underneath the surface, and the photomultiplier tubes are on top. They slightly miss the point. So we have these nice solar neutrino experiments. So how do things look? Well, there's actually a problem. For several decades, there was a discrepancy between the prediction for the flux of neutrinos from the sun, so here's the theory, and the value that the experiments are seeing. So there's the gallium and the chlorine experiments and the water Cherenkov. So there's a couple of possibilities. Are the solar models wrong? This would be concerning. You know, if we don't understand how the sun works. Are the experiments wrong? Well, there's several of them, and we have different detection mechanisms, so it's hard to believe they're all wrong. So maybe we don't understand the neutrino. Maybe there's something we're missing. I'm sorry, it seems to have looped. Okay. So along came the Solar Neutrino Observatory, or SNO. SNO was also a water Cherenkov experiment, but it was different from other water Cherenkov experiments because instead of using light water, it actually used D2O, heavy water. So it's the same as regular water, but instead of hydrogen, you have deuterium. So it was a 12-meter diameter acrylic vessel with an array of 10,000 photomultiplier tubes to view the light produced in the heavy water, and then a light water buffer region to protect the target from radioactivity in the rock. SNO actually ran in 3 phases. The first phase, the target was pure heavy water. In the second phase, it was loaded with salt for enhanced detection of neutrons. And then in the third phase, it was loaded with an array of specific neutron detectors, helium-3 strings, the neutrons captured on helium-3. So SNO was located in the Crichton mine, which is an active nickel mine in northern Ontario, Canada. It's 2 kilometers underground. You can see a schematic of the mine here, and here's the SNO site at the 6,800 foot level. For comparison, is the CN tower. And this is site in the winter. This green tower, that's on top of the shaft, which is how you get down, how you go underground. And so to go underground, you're going down with the miners because it's still an active mine. So you have to get dressed up in the full mining gear, the overalls, the helmet, the flashlight, the boots, the whole 9 yards. And so you go into the cage, which is essentially a large metal box. And if you're lucky, you're not stopping off at any stages on the way down. And they take you straight down to the 6,800 level, which takes about 3 minutes. So it's actually quite fast, rattling down the rock shaft. And then when you get down, you see something that looks like this, which is the mining tunnels underground. And you trek about 2 kilometers, probably getting blisters from your mining boots, to the lab. So the lab is a clean environment, which means that when you get there, the mining gear has to go, you go through showers, and then you put on some very fashionable overalls. And here are just a couple of pictures. So this is the control room, the computers used to monitor the detector. This is the room with the process systems, which are used to monitor the purity of the heavy water. And again, just for comparison, here's Hollywood's take. So they don't seem to care about the mining gear. They wander down in their jeans and t-shirt, why not? The scientists run the cage. I guess it's not an active mine, maybe they have no one else. And they don't seem to mind about the environment, so they don't seem as worried about contamination as we are, but I'm sure they know what they're doing. So what happens in this film is that they go underground 11,000 feet to a copper mine in India, town familiar. They open up the neck of their water Cherenkov vessel and they look inside and the water is boiling. And the point is that the increased flux of solar neutrinos is causing the water to boil. But apparently only water that is underground. So we'll revisit this. So what was different about snow? Why did the heavy water help to resolve the solar neutrino problem? Well, the other water Cherenkov experiments detected neutrinos via elastic scattering, as I mentioned. So this is sensitive to electron neutrinos and also a little bit to the other flavors. The use of heavy water meant that snow could see the interaction of neutrinos on the deuteron. So the charge current reaction, which is shown graphically here, this is sensitive only to electron neutrinos, neither of the other flavors. It actually also gives you a very nice measure of the neutrino energy, so you can actually extract the spectrum. And then also the neutral current interaction, which is when a neutrino comes in and just breaks up the deuteron. This is sensitive equally to all three flavors. So this gives you a flux of the, this gives you a measure of the total flux of neutrinos from the sun, independent of flavor. So this was the image I showed before, the solar neutrino problem. Snow's measurements resolved the issue. The charge current measurement, as I mentioned, this is just electron neutrinos. This agreed very nicely with previous experiments. The neutral current measurement, which as I said measured all three flavors, agreed beautifully with theory. So this told us that the electron neutrinos produced in the sun must be changing flavor before we detect them on the Earth.
Question. On the three type of things that you're detecting, like types of current, how do you see the signals from the previous slide?
So this was the three phases that I mentioned with snow. So this is just heavy water. So it's the neutrinos interacting on the deuteron. In all three cases, you're looking for the Cherenkov light, but the difference is that when you put salt in, you increase the capture cross-section for the neutrons from the neutral current. So you get an enhanced measurement of the neutral current signal. And then when you put in the helium-3 strings, that's actually an independent measurement of the neutral current signal because you're no longer using the photomultiplier tubes to see it, you're actually measuring them on these separate detectors. So it was an independent check of our own measurement. So this was big news. It actually hit all the headlines. It's just a couple of examples. We had essentially demonstrated that neutrinos were oscillating between production in the sun and detection on the Earth. So what this told us is that although neutrinos are produced in their weak or flavor eigenstates, the electron, the muon, and the tau, they actually propagate in physical or mass eigenstates. And because physicists are so creative, these are named 1, 2, and 3. So what that means is that neutrinos have to have mass. Because in order to get this oscillation effect, there has to be a mass difference between the three states, 1, 2, and 3. So this gives us the standard feature of neutrino mixing as we understand it. We have the three flavor states, the electron, the muon, and the tau, and the three mass states, which are a linear combination of these. And this can be described with three mixing angles, which tell you the fraction of each flavor state in the mass states. Two mass differences, the 1, 2, and the 2, 3, and one phase, which actually could potentially tell us whether neutrinos and antineutrinos behave differently. There's an additional uncertainty because neutrino oscillation actually only depends on the mass difference squared. And we know the sign of delta n squared 1, 2, but we don't actually know the sign of delta n squared 3, 2. So that means there's two potential hierarchies. 1 and 2 could be either lighter than 3 or heavier. So the mixing can be described with this nice complicated matrix. You can separate it into different sectors, and this is essentially the different sectors of neutrino oscillation. There's the atmospheric sector, which measures theta 2, 3 and delta n squared 3, 2. And this is well measured by atmospheric experiments like Super Camion-Candé, and long baseline experiments. There's the short baseline sector, which has this angle θ13, and up until very recently, this was actually unknown. All we knew was it was very small. But about a month ago, we actually had the first definite measurement of this with a 5 sigma significance from the Dia experiment. And it's actually not quite as small as we thought it was going to be. And then the solar sector, which is measured by the solar neutrino experiments like SNO and the Canlan's reactor experiment. So this seems like a fairly complete picture of neutrino oscillation. So what's left? Well, there's one very fundamental question, which is the actual nature of the neutrino. Is the neutrino its own antiparticle? If it is, then it's something called a Majorana particle. And this will be unique to the neutrino. No other particle has this property. And if this is the case, it could actually give us a mechanism to explain the asymmetry in the universe between matter and antimatter. Then we'd also actually like to know the absolute neutrino mass scale. We have ideas of the mass differences, but we don't know the absolute scale. Neutrinos are very useful as a probe. We can use them to see into the center of the sun, into the center of the Earth, into distant supernova. And then we would also like, just to increase the precision on the measurements of neutrino oscillation parameters, this allows us to look for places where we don't necessarily understand the full picture yet. So I've talked about the SNO experiment, very successful, resolved the solar neutrino problem. SNO was decommissioned in 2008. We returned the heavy water to the Canadian government, so the space was going begging. So along came SNO+. We said, thank you very much, we'll have that. So we're reusing the detector, the same vessel, the same photomultiplier tubes, the same location, with a few minor upgrades, but the major change is that instead of heavy water, we'll have a liquid scintillator target. And the difference there is that liquid scintillator has a much higher light yield. What that means is you have a much better energy resolution, and you can go to lower thresholds. What it actually also means, because we'll have the same light water buffer region that we had on SNO, there's actually quite a big difference in refractive index between the scintillator and the water, and it might potentially give us the world's largest spherical lens. So you can simulate this effect. This is a simulation of our vessel. The purple is the acrylic vessel. Each of these little red spots is the photomultiplier tube. And if you just line the cavity with a nice checkerboard pattern so you can see the effect, then you get something like this inside the vessel. So SNO+ is under construction at the moment. We hope to be taking data, first data towards the end of this year. It's located in the new SNO lab facility, which is basically an extension of the original SNO lab underground. You can see here, this is the SNO cabin. You can see the SNO detector there. And this is what existed before for SNO, and this is all new. So it's been extended significantly over the past 2 years, and there's actually now several other experiments located down there as well. This is a picture of one of the new caverns, for example. This one's called the Cube Hall. The dark matter experiment that I work on is going to be located here. This is just a picture of the celebration when they first opened the lunchroom. And anyone who goes to Canada will know that the best part is the Tim Hortons donuts. And then this is just another image of the facility underground with a view of the surface of the mine. The other upgrade on site is the new surface building. When I used to go to do shifts on SNO, we were located in trailers parked on the surface, in car parks basically in the mine. So you had your laptop on the rickety desk, and if you were doing graveyard shift, occasionally you could hear the bears outside. So the physics program at SNO+ is extensive. The primary goal is the search for neutrinos double beta decay, which will give us a handle on the nature of the neutrino. We then have an extensive solar neutrino program. We'll also be able to look for reactor neutrinos, geoneutrinos, and, if we're lucky, supernova neutrinos. So I'll now just give you a brief introduction to each of these. The process of 2 neutrino double beta decay second order process where essentially two neutrons in the nucleus undergo beta decay at the same time. So you get two electrons and two neutrinos. If the neutrino is its own antiparticle, if it's Majorana, then the two neutrinos can actually essentially annihilate inside the nucleus, and the only thing that gets out is the two electrons. So the spectrum for the two neutrino double beta decay, it looks qualitatively like the familiar beta decay spectrum, the continuous spectrum. And in the case where the neutrinos annihilate, because you don't have these extra particles to carry away the energy, every event will be right at the endpoint. So the signal we look for is a peak at the endpoint of the spectrum. The predicted rate of this decay depends on three factors. There's a phase space factor, which depends on the isotope in question, and you can calculate that. Well, the theorists can calculate that. There's a nuclear matrix element, which can be calculated, but it has a lot of complexities to it, and there's some uncertainties associated with it. And then there's the effective neutrino mass. So this is given by the linear combination of the mass eigenstates using the matrix that I showed earlier. So this is where you get a handle on the absolute neutrino mass scale. And it also actually depends on the hierarchy, because, for example, you'll see, we know that beta 1,3 is small. This is by far the smallest of the mixing angles. So the contribution to the effective mass that you're seeing from the M3 state is very small. So in the normal hierarchy, where M3 is the heaviest neutrino, you're getting the smallest contribution from the heaviest neutrino. So you're going to get a fairly small effective neutrino mass. So one of the most important questions when designing a neutrino double beta decay experiment is what isotope to use. There's only a few isotopes known to undergo the process of two neutrino double beta decay. You probably want to pick one of those. And then you want one that's going to give you a high rate of zero neutrino events if they occur. So there's a number of factors to consider. The phase space factor, you want it to be as high as possible. This is actually the inverse, so you want this to be as low as possible. The nuclear matrix element, you want to be as high as possible, although, as I mentioned, there are uncertainties in this, so you don't want to weight that too heavily. And then the natural abundance, this just tells you how much of the isotope of interest there is in the naturally occurring element. So again, you want this to be as high as possible because you don't want to waste your time with all the other isotopes. And then the Q value, the endpoint of the decay, this is where you're going to be looking for your signal. So this is very important because you want it to fall in a region in your detector where you don't have a lot of backgrounds. So it's going to be easy to see the effects. So SNO+ shows a neodymium. It has the highest endpoint, which means it's in a nice, relatively background-free region, and it has the most favorable phase space factor. So this seemed like a good choice to us. And the way we do it is that when we have scintillator in the detector, we essentially just dissolve the neodymium in the scintillator. The advantage of this approach is very simple. We already understand the detector. We've been running it for 10 years. And we'll be able to run it with scintillator before we even put the neodymium in, so we can understand and characterize any backgrounds and the detector behavior before we even put in the isotope. So we have a source in, source out comparison. So this is just an image of what the signals will look like in the region of interest. These are the different backgrounds. You have a couple of radioactive contaminants. There's thallium-208. Bismuth-214 in red. The major background is actually from the two neutrino double beta decay. This is this purple one. And then the boronate neutrinos are actually a fairly constant background to all of this. So if there's a signal, then we would see something like this. You get a little bump at the endpoint, and it's not a delta function because your energy resolution smears that, which is why it's very important to have good energy resolution. And the significance of the signal is essentially the difference between this dashed line and this solid line. So this shows you the phase space of the potential neutrino mass. So this is the lightest neutrino mass, so M1 in the normal hierarchy. And this on the y-axis is the effective neutrino mass. And the different regions show where these values could fall based on our current knowledge of the oscillation parameters. So there is actually a controversial claim for detection of this process. It's, well, controversial is putting it nicely. So really we need to verify that. That sits sort of up here somewhere. The current generation of experiments have already made measurements in this sort of green band, and the forthcoming generation will sit in this blue band. Snow Plus, in its initial configuration, will be completely competitive with other experiments. And if we can get enriched neodymium, which means we can increase the fraction of the isotope of interest compared to the natural element, then we can lead the field. So I mentioned that we can also look for reactor neutrinos. This is just a little excerpt from Google Maps that shows the Snow Plus site in Sudbury. There are actually two nuclear reactors fairly close to Sudbury. The baseline is about 200 kilometers. And the nice thing about that is there's only two of them, and they're at a similar baseline. So you actually get a very well-defined flux and a very clear oscillation pattern. The signal for reactor neutrinos, as it was for Einstein, is the antineutrino on the proton, giving you the prompt positron and the delayed neutron. So the signal looks something like this. This is as a function of energy, this number of events. And this is the prediction for what we'll see in Snow Plus. And you can see there's two very clear oscillation minima in our spectrum. The major competitor for this measurement is the Camland reactor experiment. And they've made some beautiful measurements already. It's been running for about 10 years. But the advantage we have is this nice, simple configuration. Camland has a dozen reactors or more, all at different baselines, so it smears out the shape of the spectrum. You can see here's their spectrum. So that actually gives us, although our statistics are lower, it gives us a similar sensitivity to the oscillation parameters. Geoneutrinos, these are electron antineutrinos from radioactive decay in the Earth. And again, actually, the Camland experiment and Oryxino, which is another nickel scintillator experiment, have made measurements of these. But it's actually very interesting to have measurements in different locations on the Earth's surface, because the measurements vary depending on the ratio of the thickness of crust to mantle. So a measurement at Snow Plus can help us pin down some of the models of heat production in the Earth. And actually, the major background to a geoneutrino measurement is the reactor neutrinos. So Camland, that had this very high reactor neutrino flux, that's the reactor neutrino flux in beige. And you can see the geoneutrinos as the red, just sort of sticking out behind it. In Snow Plus, the reactors follows this line, and then down the red line, and the geoneutrinos are very implicit on top of that. So, coming back to solar neutrinos, I mentioned that Snow Plus has a wide program of solar neutrinos, but is there really anything left to do? Didn't we solve the solar neutrino problem already? So, what's left? Well, this is the current picture of, so here was the theory and the different measurements. And you may notice there's quite a lot of spread between the different experiments. And in fact, if you look carefully, the spread actually seems to be energy dependent. The guys up here are kind of low, the guys down here are a little bit higher. So, maybe there's something else going on. There is. The idea is that solar neutrino oscillation is actually complicated by the interaction of the neutrinos with the matter of the sun as they propagate out from the core. And what happens is that the electron neutrinos, because they can interact via charge current as well as neutral current interactions, you actually get an additional suppression of the electron neutrinos, but this effect only kicks in at the high energy end. So at the low energy, and this is the survival probability of the electron neutrinos, so how likely an electron neutrino is to still be an electron neutrino when you detect it on the Earth. At the low energy end, it's dominated by vacuum oscillation. But because the oscillation length is actually much smaller than the distance between the Earth and the Sun, you average over the oscillation length and you get roughly a half. At the high energy end, you get this additional suppression and you get roughly a third. So we have measurements in both these regions. Snow made measurements here, the other water triangle experiments. the radiochemical experiments are down here, but we have nothing in this transition region. And this is actually a very interesting region, which I'll get to in a minute. The other effect actually is that these matter effects predict that we should see a difference between the solar neutrino flux between day and night. The reason being that at night, the neutrinos of course are passing through the entirety of the Earth to get to your detector. And as they do so, there should be some regeneration of the electron flavor. So you should see a difference. So I mentioned this transition region between the vacuum and the matter-dominated oscillation. And this region is actually very sensitive to a lot of potential new physics effects. I just give a few examples here. There's a lot of non-standard physics that can alter what this region looks like. For example, sterile neutrinos, there are all sorts of models and they can do pretty much anything you want. So you can even get like these little oscillations in that region. Or mass-varying neutrinos, which is an interesting theory where the neutrino mass depends on the local neutrino density. And again, this it just changes the shape of the survival probability in that region, so that looks quite different. So we would really like a measurement in this region so we can understand exactly what's going on. You know, is it standards? Is it just the standard matter effects? Is it what we think it is? Or is there some exciting physics effect? So this motivated the Water-Trenkov experiments to push lower in energy to see if they could see this turn up in the spectrum. The SNOW experiment led this push with the low energy threshold analysis, affectionately termed LETA. By pushing lower in energy, you of course get more sensitivity to the low energy end of the spectrum. You actually also in SNOW get significantly more neutral current statistics, roughly 2/3 more statistics. So from this analysis, SNOW actually halved their uncertainties on the boron-8 flux. You can see the comparison here. This was the original SNOW measurements, and then these were the new SNOW measurements. And the uncertainties are now less than 4%, which is actually about 1/3 of the theoretical uncertainties on this neutrino flux. So the onus is now on the theorists to do better. The other thing that comes out of this fit is a direct fit for the neutrino survival probability. So this is where we would like to see the survival probability turning up as it gets to low energy. That's what we expect. It's not what it does. So you can see the black line is the result, and the orange band is the uncertainty on the result. This is actually consistent with flat, but it's clearly not evidence for a turn. So this was slightly frustrating, a little bit tantalizing.
So the orange line is what?
The orange band is the uncertainty on the black line.
What?
The uncertainty is how well you know it. So this motivated other experiments to have a look for the same thing. The Borg-Zeno experiment, the Nicholson-Plato experiment, pushed lower in energy. The red points are their data. The bands are the theoretical prediction. And you can see that again, they actually turned down a little bit relative to the prediction. And then this is the Super Cameo-Kande experiment, 2 different phases of that experiment. And again, you can see their spectrum is very flat. There is no evidence for a turn. So all of this taken together is not statistically significant, but it's interesting. There have been several papers postulating potential new physics effects that might explain it. But basically what it tells us is we need more information. So this is what the survival probability looks like as we understand it. This is the current best fit shape. This is the result from all combined solar neutrino experiments for the low energy solar neutrinos. This is the SNOW survival probability. And so this region is where we would like to know what is going on, because it looks like they're turning down relative to this best fit. So you can also take these results to actually determine the values of the oscillation parameters. If you combine all the solar neutrino experiments, then you get the current best value of θ12 and delta m squared 12. And in fact, if you compare to the Camland reactor experiment, you can also get a measurement of θ13, this third mixing angle, which, so we produced this result last year before the diobey experiment saw their 5 sigma result, and they confirmed our result very nicely. So there's a lot to understand about neutrinos. We can actually also use neutrinos to understand the sun. I mentioned we can use neutrinos as a probe. Historically, one of the beautiful things about the standard solar model was always how well it agreed with helioseismology. The standard solar model makes predictions for the speed of sound in the sun, and then you can compare that to helioseismology, and there was a beautiful agreement. However, recently, new measurements of the metallicity of the sun, which is the abundance of the heavier elements, produced a new value, a lower value, and that, when you take it as input to the standard solar model, it actually changes the prediction, and now there's a disagreement with helioseismology. So we would like to understand this. And one way to do it, probably the best way to do it, is to measure the CNO neutrinos. The flux of these neutrinos depends linearly on the metallicity of the sun, and the predictions for the different models differ by about 30%. So you don't even need a particularly high precision measurement, you just need to see them. And the metallicity does also affect the PP neutrinos. For example, the boron-8 neutrinos that Snow saw. But you can see these are the predictions for those boron-8 neutrinos for the 2 different levels of metallicity. See, it's not a big difference. And the Snow results actually fell right bang in between the 2 anyway. So we don't really get a handle there. However, the boron-8 neutrinos actually depend on similar environmental factors in the sun to the CNO neutrinos. So a precision measurement of boron-8 can be used to reduce the uncertainty on the CNO, reduce the theoretical uncertainty on the CNO neutrinos. So Snow made measurements at the high ends of the solar neutrino spectrum, we measured the boron-8 neutrinos, and with LISA we push lower. Snow Plus should be able to make measurements across the entire spectrum. So that will allow us to test these oscillation models and look for new physics in the transition region. Just to overlay it, this is that survival probability curve I was talking about. So what we really want to look for is these PEP neutrinos and the low energy boron-8 neutrinos. So we can really map out the shape of this curve. We should be able to measure the CNO neutrinos and resolve solar metallicity. And then a slightly more ambitious goal is to measure the PP neutrinos themselves, which would give us a direct test of solar luminosity. And there's John McCall put it in sort of the god of solar neutrinos. This is really the gold ring of solar neutrino physics. So there are a couple of other solar neutrino experiments. So why Snow Plus? What do we have that they don't? Well, one of the major backgrounds to these measurements comes from carbon-11, which is a beta decay, but it's produced in the detector by cosmic muons. The flux of cosmic muons goes, this is a log scale, it goes logarithmically with depth. So our major competitors, CAMLAB, is located in the Kamiota mine. Xeno is in Gran Sasso, and then his Snow Plus is over. So you can see we're a lot deeper. That means the muon flux is a factor of 100 lower than at Xeno and 600 times lower than CAMLAB. So this, for example, is a simulation of signals in Xeno. This blue line is the PEP neutrinos, which we'd like to measure. And the way you look for them is you look for this characteristic edge in the spectrum. But their carbon-11 background, this black one, sits right on top of it, and it's very high. So they developed a special cut to reject the carbon-11, but in doing so, they actually reject half of their signal as well. In Snow Plus, not only is the carbon-11 much lower, but the signal is also higher. So we won't need to develop this special curve. And then size helps. Snow Plus is very large. We have 4 times as many photomultiplier tubes. That means we should have better energy resolution. And this is roughly the scale. We have about 3 times as much scintillator in our target, and the fiducia volume, which is the area that you actually analyze, is more like 5 times as big. So statistics help. So Snow Plus's prospects, we should be able to do a 10 And that should be enough to really give us a good idea of what is going on in this transition region. This is just some of the signals and backgrounds and a sample fit from our sensitivity studies. We will also be able to reduce the uncertainties on the oscillation parameters, but this is really a bonus. What we're looking for is the potential new physics in that transition region. And in addition, a measurement of CNO neutrinos from SNO+ in combination with the boron 8 measurement from SNO should help us resolve the solid uncertainty. So, what is the status of SNO+? Where do we stand? I'll just give you a few highlights of what we're doing at the moment. So, for SNO, because we had heavy water in the vessel and a light water buffer region, we actually needed load-bearing ropes to hold the vessel. In SNO+, because we're filling with liquid scintillator, which is actually less dense than the light water buffer region, we need a hold-down rope net to stop the vessel bobbing to the surface of the cavity. So this is now, this has been installed. This is a simulation of the pressure that the ropes will put on the vessel. This is looking up from the bottom of the vessel. This is the neck, this is the rope net, and this is the guys actually installing it. We are in the process of actually sanding the inside of the acrylic vessel. So this is the 12-meter acrylic vessel. This is a couple of photos of a ladder deployed actually inside the vessel. This makes me nervous every time I look at it because the equivalent of one handprint on that vessel would ruin the experiment because there's enough potassium in one handprint that it would just swamp any of our signals. So we have to be very careful. But the idea of sanding is because the vessel's been sitting in air for 3 years, we want to just take off a micro-thin layer on the inside to get rid of any potential contaminants. We have completed the electronics upgrade. This was all done at University of Pennsylvania. These are some of the new electronics boards that have been installed on site. Here they are being installed with our careful tools. These were tested recently. In fact, we had our first successful air fill phase. So we filled the detector with air. And then we go dark because the photomultiplier tubes are very sensitive to light, of course. And we turn the high voltage on the PMTs on for the first time in over 3 years. So this had two purposes. One was to benchmark the status of the detector. We want to know how many tubes have broken while they've been sitting off. And also to stress test the electronics. So you can see some of the best part about the new electronics is all the fancy LEDs, of course. So you can see some of the electronics running in the dark conditions. And this also gave us a chance to test some of our new tools. So for example, this is the event display in action. You can see here's an image of the detector, and each of the colored spots associates with a hit PMT. In this case, the different color is the time at which the PMT was hit. And this is actually something that Hollywood got right. So this was their event display. This actually looks pretty authentic. This looks fairly similar. But they figured out something that we haven't yet, because they can apparently see neutrino tracks in their water triangle detector. So the other thing that we've done is install a set of cameras. We installed these at the radius of the photomultiplier tubes. What these will allow us to do is identify the position of any calibration source inside our detector to centimeter level precision, which is incredibly useful. It also gives us some great photos of the inside of the detector. So this is the acrylic vessel, the 12-meter acrylic vessel. That's the neck up there. That's about 5 foot wide. You can go down here. And these are the photomultiplier tubes arranged in panels. And that's just another picture looking around the side of the vessel. So the program for SNO+, we will do some further airfill running this summer once we complete sanding. We will be sending a lot of people to site this summer in order to sand the vessel. If anyone fancies going inside a 12-meter vessel 2 kilometers underground, get in touch. So we hope to turn on for the first time towards the end of this year. We will actually initially do a light water phase. We'll fill the vessel with light water. We actually need to do that because to fill with scintillator, you have to displace the water rather than just filling with scintillator to begin with. That actually allows us to do a very nice nucleon decay measurement at the same time, so the bonus. We'll displace with scintillator early next year and start with our initial solar phase, and then the double beta running will be probably early 2014. And we'll be able to do the geoneutrino and reactor neutrino measurements throughout the scintillator phases. So this is just a figure that one of my colleagues likes to show, which is all of the solar neutrino experiments as a function of time. So when the data is taken. So you can see the chlorine experiment, first solar neutrino experiment, is Snow. Snow is the blue one. There's us. And if you fit a line to this, it actually comes out with a slight positive gradient. Okay.
What was this measurement of?
This is the measurement of solar neutrinos. It's normalized to the standard solar model. So it's.
You think that increase is real?
This is a slightly facetious figure. So this, what my colleagues like to say is, this is motivation for why we really need to keep watching the sun, because who knows what's coming next. But the other thing that you could do is figure out how far you need to extrapolate in order to boil water with solar neutrinos. So I did this calculation, including the effect of oscillation, and we've got a little while. I don't think we need to worry. So just to conclude, I hope I've given you a brief overview of the properties of the neutrino, and then described how the Snow experiment resolved the solar neutrino problem. Introduced you to Snow Plus, which is a multi-purpose neutrino experiment, which may potentially be able to tell us the nature of the neutrino itself, as well as give us a really thorough understanding both of the sun and actually of the Earth. And don't believe everything you see on TV. Thank you.
And now, how are we on time? We're good?
Yeah.
We're good, okay. So does anybody have any questions? Yes.
So in Japan, they've turned off a lot of their nuclear reactors. So how is that affecting, like, trying to study nuclear neutrinos?
Well, so actually CamLab will be able to make a really nice geoneutrino measurement. I mean, they've already got 10 years worth of the reactor data, so
Okay.
it's actually very nice for them. It means they can do a sort of reactor off calibration.
You said that, I just wondering, like, you said that if the neutrinos have their own antiparticles, why is that special?
So the neutrino is the only particle for which that can be true. If a particle is charged, it immediately can't be true because the antiparticle has the opposite charge. If it is true for the neutrino, then it gives us this potential mechanism by which we can explain the asymmetry between matter and antimatter. So that involves, there's several stages to it. You also actually need CP violation, which is a difference between the behavior of neutrinos and antineutrinos, and then you have to assume that there is a very heavy neutrino that was created early in the history of the universe, and that neutrino decays with an asymmetry to particles and antiparticles. Sorry. So essentially, it gives you a way to explain why the universe is now dominated by matter. It's depending who you talk to. It's a potential explanation.
So, how does, how do they change flavors while they're traveling if the flavors are different masses?
So, it's the mass eigenstates that really have the property of finite mass. The flavor state is a linear combination of the different mass eigenstates. So it's quantum mechanics. I mean, so if it's produced as an electron neutrino, for example, that's some combination of 1, 2, and 3. And then as it propagates, perhaps it's propagating as 2, and when you measure it, you measure it by the weak interaction, because it has to interact in your detector in order for you to see it, and that forces it into one of the flavor states. And the combination of the states may have changed by the time it gets to your detector, so it might collapse into a different state at that point. It's probabilities. It's all statistical.
But somehow the probability for changing depends upon the distance to which the neutrino.
Yes, so let me.
So when they first detected the lack of neutrinos in the Colin experiments, the sun was, or is, 93 million miles away. So naively, we think that there's enough distance for things to happen, so the neutrino can change from one flame to the other. But then they're now finding oscillations even over distances of 200 to 270 kilometers, right?
So these are the different sectors of neutrino oscillations. So the solar sector, actually the oscillation length in the solar sector is much less than the distance between here and the sun. So you're averaging over a lot of oscillations. For the much shorter, like the short baseline reactor experiments, for example, then you might be sitting, this is just showing, this is a simplified two-flavor picture, but you might be sitting, for example, in the first oscillation minima, and you're actually seeing that first oscillation, whereas for the solar neutrinos, you just average over the whole lot.
But these oscillations would continue to be seen over shorter and shorter distances?
For the solar neutrinos? So, the solar neutrino sector, for example, the Canland reactor experiment sees the same sector of neutrino oscillation. Their baseline is 200 kilometer-ish. So they're sitting at the equivalent of one of these.
So does it matter as the sun's rotating? As the Earth's rotating, like closer and further away from the sun?
There is a small effect, and we can actually see it. You need quite a lot of data to see it.